This conference will now be recorded.
All right, so TCP IP model and the OSI model are something that you're gonna need to have in your just everyday language, right? Understanding how to troubleshoot. This is where this comes into play. I know that I know that some of you have had this experience before. You've been at home, you've been working, and the internet goes out, and you're like, "Oh my God, why is the internet out?" What's the first thing you do? You try to go to a web page, or you try to start banging on the keyboard, or you're looking like, "Am I connected to the internet? What's going on? Is the internet on? Like, is the actual router on, or the modem is that on?" Right? But what you're literally doing is you're walking through the OSI model. And when I say that, I'm saying you're looking like what is the physical device that is holding that I connect to, that wireless modem. Is it really working? Like, is it on? Is something going on with it? Oh, I'm connected to it. Okay. Where can I get out? Right? Can I get out? Right? Or is the power out on it? Is my laptop about to die, so it's just shutting stuff down, or did I click on something? You're physically walking through that, right? And then uh, moving up the stack, I'm starting at the bottom with the physical aspect of it, because when you are troubleshooting, you should be starting at the physical layer, right? And then you move up the stack, right? So when you move up the stack, the data link layer, I kind of put that hand in hand with the physical layer, like what I'm plugged into. But the network layer, layer three, another aspect of that would be like, well, is the actual router itself getting out back to where it needs to? In other words, is it connected back up to the actual network? Is it connected back up to AT&T or Verizon or whoever you have? Is it actually talking to where it needs to talk to so I can get out, right? Did I pay the bill? Did I pay the bill? Did they shut me off? Right? You didn't pay the bill, you get no access. It'll still be green on your end, but it won't get out. Right? It'll show you that little X, like you don't have any access and we can't see you. Right? And it'll blink and just be like, "Hey, yeah, nothing's happening over here." Right? And then you move up to that transport layer where we start talking about TCP, UDP there, and then I'm going to skip all the way up to the application layer, right? Is the application working how it's supposed to work? Is it able to talk to what it needs to talk to, right? So here we see, and when I talk about this, we have these right here, but that SSH communication that you have, can I SSH to that box? Am I getting time? LDAP, you'll get this if you are on a VPN, or if you're using some type of Windows server that connects back to, say, you're on a VPN and it connects out to your job or whatnot. This is where most people start troubleshooting that you're disconnect and reconnect, or try to reconnect, but really you should be starting down here. You shouldn't troubleshoot from here down. You should be troubleshooting from here up. Does that make sense for everybody? Right. And another thing too is sometimes you have bad cables, or hardware actually goes bad, right? Sometimes it could be a bad NIC card on your laptop, or it could be a bad wireless card on your laptop. It could be a bad cord. It could be a bad cord that your actual wireless device is doing, or it could be a bad coax cable, depending on what it is. It could be if you're using fiber, it could be a break in the fiber connection. Like, has anybody ever tested fiber before? Do y'all know what a fiber line looks like in your house? Like what the actual fiber line looks like? Because it should be a straight. You should be able to shine your a light down the fiber cable, and it comes out on the end. It shouldn't be a break in that fiber. Ever seen a fiber cable before?
Yes.
All right. So those that may not have ever seen one, basically that's what it looked like right there. Hopefully they had one stretched out, and that's what it looks like on the inside. But here's what I was talking about: the light on the end. All right, I should be able to shine a light on one end, and light should come out on another end. And if I don't get light that comes out on the other end, then that's a bad cable, right? So it could be that it could be a bad cable or something like that. But that's only on the fiber side. On the Cat 5, Cat 6 side, it could be a bad clip. It could be anything. Somebody could have saw something in half or something like that. Yep. Yep. All right. So also in here, when they were talking about, they start talking about IPv4, IPv6, and so forth. And we're running out of IP addresses. We've been hearing that I've been hearing that since 2000 that we were running out of IP addresses, right? I don't know, do they still do like class D IP addresses and stuff, the stuff that's set aside for the military and so forth? Is that still available? Is that still knowledge? I don't know. I haven't played with it in so long. So because it was a little convoluted on that, let's hop over to here. So here we start talking about CIDR and versus VLSM. So I'm gonna blow this up because it's a little small. All right. So this link is posted in the chat, and I mean not in the chat, but in the RHCSA class. All right. So here they talked about before like IP addresses. So when you see an IP address like this, like 192.168.0.1, right? Normally most people will ask you like, what is that? What is that? What type of uh class of IP address is that? Like, is it a class A, class B, class C, class D, so forth? And then people will ask you like, okay, well, what's the subnet mask on that? I think everyone has seen that, right? So in the class, let's go here because they actually give you a good breakdown. Let me get my mouse. There we go. Of this. So let me go back up here. Let's go to here and let me go to there. Is that it? No. Here. So look, you see here, you got 172.25.252.0/24. You see a /24 and so forth, right? But what they're showing you here, by automatically, you should be looking at this. That 24 bits are automatically on. And when I say 24 bits are automatically on, each one of these octets, right, that are separated by decimal. That's how we know it's an octet, right? An octet meaning 8, right? Each one of these are represent 8 bits. So 8, 16, 24, meaning they're all on. Meaning when I see that, it's in RHCSA channel inside of Slack. When I see that, that means all of this right here is the network portion of my network. So 172.25.252, right? And then this last octet is dot zero, right? Meaning that it's fancy, wild, and free, right? Meaning there's some restrictions on that, and some of the restrictions is not being able to use the last IP address because it's a broadcast, and not being able to use the first because it is the network, right? So let's get into this. So when we see it, right, it's saying that we have 32 bits, which we just talked about. 8 times 4 is 32. 8 plus 8 plus 8 plus 8, 4 times is 32. But it's broken up into network bits and host bits. So when we look at this particular piece here, it's broken up. If you want to call it like this, this is would it let me highlight? No. The 172, 25, 252 are the network bits, and then this dot zero are the host bits. And that's what they're showing here, right? That's what they're trying to say that is broken up. All right. So it says, as a basic definition of subnetting is dividing the network into smaller work groups. By doing this, using the IP address block more efficient, meaning that I can have a network, right? I can give you this network, but you may need to, let's look at it from this perspective. How many IP addresses do you think exist in a hospital? How many IP addresses do you think exist in a hospital? Think about all the things that need an IP address. All the things that will be needed in a hospital that needs an IP address. Think about all the IP addresses that are needed in your office, from your phone to your laptop, maybe some other device you may have. Think about everything that needs an IP address. And then just think about it this way. Would you want to have your phone traffic on the same network as your laptop traffic? And think about if you had all that traffic all on one network. Do you realize how chatty that would be, right? How much degradation that you would get as well too. All right. So we want to subnet things out because we want to isolate traffic. We want to isolate we want to isolate traffic. We want to also isolate information, right? I don't need my phone traffic and my server traffic all on the same network. I need to have those isolated. And I don't need my laptop traffic and my server traffic and my phone traffic all on the same network. But I got to figure out how I'm going to set all of this stuff up, right? All right, so it says for subnet masks are used. Subnet masks are 32-bit addresses like IPs. Subnet masks are used with IP addresses, right? So remember everything in computer language is ones and zeros, is binaries, right? So we can show subnet masks with 4 octets, 255, 255, 255.0, because this actual, what they're trying to show here is 24-bit subnet mask, which is what this would equal out to right here, 255, 255, 255.0. Because this is on, this is on, this is on, this is all ones, and then these will be all zeros. And then let me go down here and show you what they were talking about that at. Need to go back up. That was this here. Show you that example there. Right here, where they had 255, 255.0, these are all ones. I mean, this slash 24 tells me everything is on, right? And then here, they just got the IP address written out in binary, right? And so this 192 is represented here. So remember last week, well, week before last, I was like 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the 2 to the fourth, 2 to the fifth, 2 to the sixth, and 2 to the seventh. Each one of those locations represent a powers of 2, right? And so, like, how do you write 192 out in binary here, or using the representative of powers of 2? In the same way here, 2 to the 0 plus 2 to the first, so 2 plus 1 is 3. So that's how you get that, right? So that's what they're showing you. And then basically all they did now is saying, hey, here's a logical and, remember? And they're gonna end up doing like a logical and on this in order to get this, right? And they're showing you this here. But this week, we're not gonna do that. We're not gonna waste that time doing it. All right, so here, let's scroll down. They're saying, how do you represent /24 inside of uh what's the word I want to use? Cider, not cider, or VLSM. Which one I want to use? What's the proper word? I forget. Rico, what is it? When we're doing 255, is that cider? I thought /24 was cider. I could have that wrong. But
I
either
think
way,
I thought when you use the slashes, that's cider.
that's what I did too. That's what I thought that was the cider, and then
Yeah, I couldn't get off mute. Sorry.
yeah, I can't remember what it's called when we're actually expressing it out like this. It's another word. I know it's a subnet mask, but it's another word of how you express it. But either way it goes. Here's what the example is. So they're saying in our first subnetting example, we will use 192.168.5.85/24 address. Let's determine the network and the host part of this address. So when we scroll back up here, they're talking about the host part and the subnets. So let's go back, see what they say. All right, they do it the long way. They take this 192 IP address and they take the subnet mask and they convert it into binary, right? And then they take that and they do an and on this and they come out with this, right? So 1 and 0 is 0. Remember that truth table that I was talking about with the logical and? This is such a long. Mm-mm-mm-mm-mm. This truth table right here. This is the logical and, like 1 and 1. Basically, they both have to be the same. 1 and 0 will always get you 0. 0 and 0 will get you 0. 0 and 1 will get you 0. So basically, all they did was they changed everything in here into binary, or what is binary representation here, and then they just did an and on it. Well, that's cool, right? That's all right. That makes sense. Who has time to do that on an exam? All right, so let's come down here. Zeros and ones. Let me see. Where is my other one at? Oh, oh, they did all the ands. That's not what I wanted. Did I use the wrong page? Oh, here we go. All right. Hold on. All right, here we go. All right. So here, this is this subnet example, and they're saying we will see our network needs, and according to these needs, we will determine our IP address prefixes. It says we use the topology below. We have a 192.168.1.0 with a /24. So what is /24 if we had to break it down? It would be 255.255.255.0. You all got that, right? Maybe you should go do something. Let me, because I don't think you're gonna get what I'm trying to say. I think y'all need to look at some representations. Let me pull up a. Hmm, this should work. No, I don't want that. I want this. And we'll cancel
Hey, Tam, I think
that.
what you were trying to think of earlier was octet instead of subnet mask, or in addition to subnet mask, octet, the last octet.
No, what I tell it's a way it's represented. I know it's octet, but it's another word. The way, like, if you do 255.255.255.0, the way that
Mm-hmm.
looks is something else. And then if I just do /24, like, yeah, /24 would be
I got
VLSM.
you. Yeah, yeah. We
Yeah,
always just do /12, /16,
right.
/24.
And then 255.255, the way that looks, that representation is something else. All right, so let me make all of this bigger. Can I get a sizing? No? Okay, that's fine. But we can do this. Can I? Nope. All right. Let me pull up TextPad because we're gonna walk through some stuff. And I want you all to tell me what it is inside of new document. All right, so we know when we see 255.255.255.255 would equal to what? If each octet is worth 8 bits, what's 8 times 4? 8 times 4, anybody?
30 deuce.
32. All right. So we're gonna work backwards. So we do 255.255.255.128. What is that? Right? So you're saying, oh, what is she actually doing? Well, what I'm actually saying is that each one of these octets is 8 bits. Let's see, put it down right here. Each octet is 8 bits. All right. So that 255 is 8 plus another one 8. Not a star, but 8 plus another 8 plus another 8. And that equals to 32, right? But each one of these numbers or decimal numbers, well, I won't say decimals, binary numbers, actually represent 2 to the 7th. Can I do that? Yeah, I can do it that way. 2 with a caret raised to the 7th plus 2 with the caret raised to the 6th. And I'll just keep adding here. And we'll grab these. And then we're going to break down what each one of these what each one of these represent. So I'm going to go back and change this in a minute. I'm just cheating for right now. Oops, plus. And then we'll do that. All right, so 2 to the 7th, 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 to the 2nd, and then and one more. All right, and this would be 2 to the 1st and then 2 to the 0, right? So what happens is how we come up with these particular with this 255, meaning all the bits are on, right? So what is 2 to the 0? If you took 2 and raised it to the power of 0, what is that?
Nada.
That's 1.
Oh.
All right. It's all good. And then 2, let's start out with 2 to the 7. So somebody on a calculator, what's 2 to the 7? Those who know this, but what is 2 to the 2 raised to the power of 7? Anybody? Yeah, y'all got your calculators out? All right. It should be 128. 2 raised to the 6. Anybody? All right.
56.
6 should be 64. 2 raised to the 6. We'll pull out the calculator right here. All right, so let's go here. 2, where's my raise? Here we go right here. Raise to the 6. 64. 2 raised to the 5th is 32. 2 raised to the 4th is 8. I mean, is that 8? 16, sorry. 16. And then 2 raised to the 3rd is 8. Let me give you a space. 2 raised to the 4th. I mean, 2 raised to the 2nd is 4. Let's give you space a little there. And then 2 raised to the first power is 2. Keep forgetting to add space. And then 2 raised to the 0 is 2. I mean, 1. So let's go back to our calculator. All right, so we're going to add that all up. We're going to say 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 is 255. So when all the bits are on, that's what they're showing you here, that we added all these numbers up and it come to 255. So that's what all the bits are on. So that's where that 255 comes from. Does that make sense now, how they got that number? Okay. So now when I ask you, what does this actually look like? Is it going to be 32 bits? We got all these bits are on, and then this one bit is on right here. So that's going to be your /29, right? And how did I come up with that? Well, it's telling me that when I add up, whatever I add up over here, it's gonna have to be 128, but really 128 is the first position, which is 2 to the 7th, right? So how that looks is you would have a subnet mask of like how it would be written out. It would be 1.2.3.4/29. That's what it would look like. So when they're showing you right here, let's scroll back up. Where's that thing at? Right here. It's saying a /32, a /31, a /30. How do you get that? How do you get those octets like that or subnet masks like that? Right. So let's do another one. Let's do this 255.255.255.252. How would that look? What subnet? What would be the subnet mask on that? The first thing we know what the first 3 octets are on, right? We know that, right? So we know here we have 8 plus 8 plus 8 plus what? So how do we get to 252? Well, we usually start with what we call in subnet, and when we're subnetting, we have to borrow from an octet. So we got to borrow from this very last octet right here. And that octet is going to equal up to 252. So how would you get to 252? Well, good old addition, right? Anybody want to take a stab at it? I need to borrow some bits. Right? Anybody? You see what I'm doing? Right? So I had to borrow all of these bits here, right? So 1, 2, 3, 4, 5, 6. What's what's that? What's 24 plus 6? Right, 30. Right? So my IP address would look like something like 1.2.3.4/30. That's how they do that. That's how you calculate it. You're borrowing bits, right? I have this last octet over here, and I'm borrowing bits from that octet to give me my /30. Now, when I borrow these bits, right? What they were showing you here, there once I borrow these bits, I'm actually getting where is it at? It's up here. I'm actually getting the number of subnets I can have and the number of hosts that I can have on those subnets. It's giving me everything that I need. All right. Now, the number of hosts that you can have on each subnet and the number of subnets you can have. So back to our hospital example, we need to define, again, we wouldn't even have to go that far. We need to define, like, well, how many servers do we currently have on our network, right? And the growth potential we want to have, the number of phones that we have on our network, and if we got any new hires that are coming in, right? You've never been to a place where they hired just 10 people and then didn't grow, right? At some point they grow. So you don't want to have to recalculate this subnet all the time. You want to leave room for growth. Does that make sense to everybody? Let's go down here. All right. So here, now this should make a little sense, right? They're saying I got 4 subnets, right? And it's saying that I got 28 hosts on one subnet. I got 52 hosts on one subnet, 15 hosts, and 5 hosts on the subnet, right? It says there are 4 subnets, and each subnet's host address are host addresses need is also given. Subnet 1 through 4. To overcome subnetting issue, firstly, we need to determine the host bits for each subnet, right? For our first subnet, we need 5 host bits, right? How did they come up with the 5 host bits? Remember, everything is in a power of 2, right? So going back to our example, right? Right? 32, right? That's where they came up with that at. 2 to the 5th is 32. And they said this means that there are 32 minus 2 usable host addresses, right? Because you can't use the first and the last, right? It says for our second one, we need 6 bits because 2 to the 6 is 64. We go back to our example, 64, boom, right? That's 2 to the 6 right there, right? So that means that it says this means there are 64 minus 2 usable host addresses on that one. And it says now let's look at the third one. It's 15. What will we use? Remember, you got to leave 2. So I wouldn't use 16, I would use 32. But I could be wrong, but let's find out. Yes. See? Because you gotta leave. We can't use the first and the last. If we did uh just the 16 here, right here, 2 to the 4th, we can't use the first and the last. We only, like, 16 minus 15 is 1. We need 2. We need the first and the last bits. We need to leave those for our IP addresses, right? For our first and last, for our broadcast and for our network, right? All right, so that's the 5th one. It says you can think we can use 2 to the 4, but we can't. because of the addresses, because one of the addresses is used for the broadcast and the other one is used for the network, right? And then here it says the fourth subnet, we got 5. We most definitely can't use 4. We have to use 8, right? So here they're saying 2 to the third and 8 minus 2, which is 6, gives us our usable host addresses. All right. So now, did that make sense for everybody? How they did that? It's like, hey, I got 28 hosts, right? And it's saying, I'll go back through it one more time. It's saying that with those hosts, it says this means there are uh 32 minus 2 usable host addresses on that network, on that subnet, right? So basically, if we grow past let's see, 30, we can only add logically 2 more hosts, right? That makes sense. We can only add 2 more hosts on that network. So they could run out of IP spaces soon, right? They could run out of IP spaces soon, right? So here they're showing, now let's pick it up. For the first subnet, our subnet mask will be /27, right? Right. And then they said um 27 network bits and 5 host bits. And they're showing that all that equals to 32. Then they're showing you how they did what they did for /26. So let's talk about how they come up with this. All right. Do 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 do. Oh, where'd it go? Where'd it go? No. Where'd you just go, TextPad? I don't know where my stuff went. I was once Joan of Arc in my past life. Where did it go? Oh man. Let me look. Let me see if I can find it on this other page. Let me see if it came over here. Oh, there you go. I see it right there. Oh, there we are. Okay, cool. All right. So let's get back to their example. Does this make sense so far? Does everybody been able to keep up with this? Doing a little addition.
Yeah, I like it. Thank you, Tim.
Yeah. And
I hadn't seen it broken down like that. How you did it, with the
yeah,
caret
it's
eight
different.
seven six
Yeah.
five four three.
Yep. That's how I learned it. That's how I learned how to add real quickly. That's when you on the exam, you got to add real quickly. So everybody got it so far? Suzanne, this is good. Okay, Tunde, you got it? Okay. Russ. All right. All right, so let's get back to it. All right, so here. All right. It says that for our first subnet, our subnet mask would be /25. Okay, so let's look and see. I mean 27. Let's see how they came up with that. Let's do, I'm thinking that they're saying that they borrowed, in order to get a /27. The first things first. Well, we know that this is a /29. To get a 27 would be 255, 255, 255. And then they came up with, I guess, everything up to here. Is that right? We borrowed 3 bits. That make it a /27. So what's that? 128 plus 64 plus 32. Get my calculator out. equals 224. It should be us 27 or slash 27 if you really want to get representation correctly. So basically what they're saying is you can work backwards and guess what the actual subnet mask is, right? So here you borrowed basically you got 6 bits that you that you borrowed. So here they're saying you're working back, you got 6 bits, 1, 2, 3, 4, 5, 6. So you borrowed all of this and you would add that up. And that'll be what your subnet mask is. Does that make sense? No? Did y'all see how I got that?
Do that one more time, if you don't mind.
So, yep. So what they did was how they're looking at it is you have these 5 host bits, right? Right. Basically, you're borrowing from the last octet, right? So since you're borrowing from that last octet, right? They're saying, hey, you borrow those, you're getting those 5, basically those bits that you need to host that. So that represents the number of bits that you need to borrow here, right? So I need to borrow that 1, 2, 3, 4, 1, 2, 3, 4, 5. Right? That's how they came up with that. 1, 2, 3, 4, 5. Yep. And they add that all up, and that's how they come up with this subnet mask. So let's go down here so I can show you what I'm talking about. All right. I'm gonna skip that for right now. All right, here's the router. Here are the router interfaces with the IP addresses. So for each subnet, one IP address will go to the router. Remember, we're given 192.164.1.0/24. Let's divide this prefix according to our above values, right? Let's begin with the biggest network. If we use /26 in the biggest network, right now, so I guess I would consider this probably the biggest, right? Because you got 52 hosts on it. If we use /26, right, it would look like this: 192.168.0/26. Then we will have 4 subnets. Then the given subnet was 24, and our new subnet subnet is 26. So 24 minus 20, 26 minus 24 equals to 2, and 2 raised to the second gives you the 4 subnets. So this is how they're breaking it down. All right. So we start out with this right here, 192.168.0./24. And that /24 has to be subdivided up to accommodate these 4 networks. Does that make sense so far?
Mm-hmm. Mm-hmm.
All right. Everybody, this is sort of Rico, everybody else that makes sense. We're gonna take that and we got a network, and we gotta subdivide. We got our IP address, basically, or our network IP address, and we got to subdivide it into 4 parts. Does that make sense? Does everybody see that? No? Okay. Okay. All right. So now it says that we have to divide this up into 4 parts, right? Because we need 4 subnets. It's saying that this representation of 192.168.1.0/26, then we will have 4 subnets. So let's look at /26. What does that look like? Let's go here. So /26. First thing first is we know we have 255 all the way across because of the represents 24, right? And then they say a slash 26. Well, that sounds like they're borrowing 2 bits from here because it's 24 plus 1 is 26. You got that part, right? Because because let's put it like this: the number of bits that I borrow represents the number of networks that I have. The number of bits that are left over represents how many hosts I can have on each network. Did that make sense? So I write it down. Number of bits borrowed equals number, I should say, the number of networks I can have. Number of bits left equals the number of hosts per network. Now, does that make sense? So, what you're seeing here is I borrowed 6 bits right here, right? And then I have what we have bits left over, right? Are y'all following this? I'll borrow bits from my last octet. That gives me the number of networks that I'm going to have. And the bits that are left over, those are the bits that are going to be that are going to say how many hosts I can have on that network. And that's what ironically, in a about way, is what they're trying to show you here. Subnets and hosts. When I borrow, that means I'm borrowing so I can create my number of networks that I want to have. Whatever I have left is the number of bits that I can have on each one of those networks. So let's look at it. So right here, they're saying, hey, let's look at, this one. The first octet, we need 5 host bits. With the 5 bits, we can have 2 to the 5th is equal to 32 addresses, and then we minus that. So you remember that, right? Scroll down here. When they're doing this one, they're saying, hey, we have 4 subnets that we need to create, right? Given that the subnet was a slash 24, and we need our new subnet is slash 26. So 26 minus 24 is equals to 2. And 2 raised to the second is 4 subnets. And then they use the slash 26 for all of them, but these are the network addresses for each one of them. .0, 64, 128, and 192. How do they get them? Do you see how they got that? It's okay to say no. Am I on mute?
They go up by 64-bit graphics every time.
Right. Are y'all seeing that?
I'm surprised I'm really catching on with this being my first lesson. I can't believe I get it.
Okay. So is everybody else tracking here? Remember, everything in the world of computers is in zeros and ones until you start getting into quantums, and that's something totally different. But in the world of computer, you're 2 to the 0, 2 to the first, 2 to the second, all the way up 2 to the 7th is your friend. And understanding how subnets and networking work is going to be super important. So here, let's begin with our biggest network, slash 26. With 192.168.1.0 like this, then we will have four subnets, right? All right, so let's go down here. We will use our first subnet 2, 192.168.1.0 slash 26. This is this one here. And now for the first and the third subnet, let's use the second block, which is this one, and then divide it again. So when they divide it again, listen to how they do that. In order to get more, I gotta borrow, right? If we divide it by borrowing a bit again, then we will have we will have two subnets. So they have to steal, right? Every time I borrow, I'm creating more subnets. Whatever is left is how many hosts I can have on each one of those subnets. That's really what you got to remember. Every time you look at something like this right here, right? You say, "Oh, okay, I borrowed 3 bits, right? Because 128 plus 64 plus 32. Let's double verify that. 128 plus 64 plus 32. Oh, I did something wrong because that ain't right. 128 plus 64 plus 32. 224, right? So I borrowed 3 bits, right? So basically, where is it? All right, so I borrowed 3 bits. How many bits in total inside an octet? You should know this is 8 bits, right? So 8 minus 3 is 5. 5 bits left. So that equals to the number of hosts per subnet. And what you basically doing is 2 to the 5th, which is 32 hosts per subnet. And that's what the class didn't show you. I borrow, I'm creating networks. What is a network? A network is gives me the ability to one have smaller devices. Like, I don't know if you ever paid attention when y'all are sitting at home and you put your laptop on your network, you put your TV on your network, you put your phone on your network, you put your printer on your network, you put uh, some other device on there. They got to get an IP address. All right. Normally, on your home devices, you can go up to 254 devices on your network, right? Because you're probably a slash 24 at home. Now you can get fancy with it and say, well, I don't want to have, and some people do this, I don't want to have that many IP addresses out there for my network. Some people go ahead and say, if you don't have no static IP, you ain't getting on my network. And I'm gonna link that up by a MAC address. Have y'all ever seen a MAC address before? Do you know what a MAC address looks like? So right here, a MAC address is a 48-bit hexadecimal address. So in the class, let me see. Hopefully, my lab hasn't died on me. Oh, it did. No, I did create it. Oh boy, but that's fine. I'll create it now. Oh, I created it in 8.2. Hold on. Let me switch over to 8.2. I thought I did. Guess not. But anyway, it's gonna do its thing and I'll show you a MAC address. But this is a example of it. But there are unique identifiers. So let me say this. Your MAC address, your NIC card vendors, say, and when I'm talking about your NIC, I'm talking like your Broadcom, what's another one? Broadcom, not Dell, NIC card vendors. Yeah, Cisco, Broadcom, D-Link. I forget the other one. It's another very popular one. Starts with an N.
Go to
Not
images, Tim.
not Netgear. Go to who?
Images.
Oh
Just
yeah,
that
yeah.
way people see it if they don't physically do it.
Yeah, I'm gonna show it to them. But Netgear, they all have what we call unique MAC addresses. So when they showed up here, usually you can identify them with the first, I think the first one, two, three, four, five. Yeah, the first 6 octets are truly like Broadcom has their own. Netgear has their own. Cisco has their own. So now what he was talking about when we go to images, and that's a horrible image. Hopefully I can get it a little bigger. That's what it would look like on a Windows box. A MAC address there. On your Linux box, you can just type IP space A and it'll give you your MAC address. It's still coming up here. I was gonna show it to you. And each vendor has their own set. I knew Dell had got acquired Force 10, yeah. So we're gonna wait for that to come up so you can see, right? And then let me see. Then they divide it again. They keep borrowing more bits in order to subdivide this into smaller and smaller and smaller. So variableness of that mask is the meaning is its meaning is using subnet of subnets or dividing a network into a smaller network with using different subnet masks. And so here, that's what they were showing you here. They was doing subnets of subnets. So if I needed more, I can divide. I can keep borrowing bits, right? But it's only so many bits you can borrow, right? It's only so many bits you can borrow, and that's only because the way this one was done, this 192.168.1.0, and then they were doing a /26. But you could also have you could also did 192.168.0.0, and that gives you a wider range of networks and a wider range of IP addresses to use, right? Because now we have more than 254 devices that we may need. We may need to put 7,000 devices on there. We may need to put 6,400 devices on our network and still have room to grow, right? So this is going to always be with you if you're doing like DevSecOps, especially if you're working in Kubernetes, right? Because each container is endpoint, it's going to have an IP address, right? It's going to have something to relate to it. It's the pod is going to have an IP, right? And this is posted in the chat in case you wanted to, I mean, inside of the class in case you wanted to look at it. But I think it got some little fundamentals in here. They got some, uh, you know, this is just going over on a DNS server, like how you would implement that on a Cisco switch. But my suggestion would be is like what explain DNS. And there are a lot of things out here that tell you like how DNS works. When would that question come up? That question would come up on an interview. If somebody asked you, like, if you typed in google.com, what happens? Or if you type in msn.com, what happens? How does your browser know to go to msn.com? How does it know to go to that? So there's a DNS name that's associated with an IP address that leads you to this server. So imagine if we didn't have DNS, you would have to remember all the IP addresses to get to all these different servers. So can you imagine if you had to remember IP addresses of websites that you want to go to, right? But you don't. You remember the actual DNS name, the domain name, right? Oh, Nick cards. Let me see. Is it up yet? No. Mm, 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 mm. So this is old school. Nick cards. This old school right here. With the wireless card that used to hang out on the back of your machines. Those are what Nick cards look like, right? Um, Here's an example of a fiber card. So we have our SFPs that we stick in right here. But basically, they would look something like this, right? Oh, that's not a good picture. Let me blow it up some. And you have your fibers that you pull in here, and they sit on the board right here, right? All right, and then um, there's also I don't think anybody. I don't know. Do people use InfiniBand boards anymore? InfiniBand switches. Anybody use those? Yeah, I guess so. That's what they look like here, right? So you're asking, why do I show this? These are what data centers are made of. This is what data centers are made of, and they're still building data centers. That's one job that's never gonna go anywhere. It's never gonna go anywhere. Uh AWS Outpost server. All right, so let's look at the images of an AWS Outpost rack. I want to see a full view. This is okay. Oh, cool. Right. So as you can see, this is an AWS Outpost. Basically, this is one of their servers that you can house in your own data center that will connect back up to AWS. However, if you don't want it to, you don't have to. You can be totally isolated and pick and choose what type of software you want to have enabled on this particular rack. It mimics everything that AWS has, all the services that they have inside of, say, AWS console, right? And as you can see in this rack, you're gonna need power, you're gonna need NIC cards, you're gonna need some fiber, you're gonna need everything. Basically, they have people that actually come out and hook all this stuff up and they maintain it for you or whatnot, including the servers and everything. But I think there was at some point of time someone talking about you can get AWS Outpost certified. Look at the rack. So here. Oh, here we go. Sound in my ear.
We're really excited about all the interest and feedback we've received from customers since pre-announcing Outposts at reInvent 2018.
All right.
In this video,
as you can see up here at the top, the switches, you see the fiber cables right here, right? Up here at the top. And then you see the switches and the routers and so forth. Let me see, do they have...
We want to give everybody a deeper look into what an Outpost is and how it works.
I'm not seeing the video too.
Some other features.
There
The
we go.
servers are almost...
What'd you say now?
I was saying I'm not seeing the video.
Oh, you don't see it? I'm looking right at it on the screen. Everybody, can y'all see the video? Okay. Yeah, everybody sees the video.
Yeah, it's not playing though.
almost identical to what we'll be shipping later in 2019. You may notice there's a lot different about an AWS Outpost compared to the normal hardware that you've worked with in the past. That's because an Outpost consists of the same hardware we use within our public region data centers, and we spent the last 12 years optimizing the rack design to deliver the best possible experience for our customers. The rack overall is 24 inches wide by 48 inches deep and 80 inches tall and comes with casters. So even though the insides are very unique, the rack should roll easily into any standard data center position you have available. Our racks come fully assembled and ready to be rolled into their final location. Within our data centers, we simply plug in power and networking, and then automation takes over, making EC2 instances available after performing burn-in testing. We have replicated this experience with AWS Outposts, and once you bring networking and power to the rack, the build process is fully automated. The first thing you might notice about this rack is that there's a bus bar in the back and a power shelf in the middle. Typical commodity servers have power supplies in every server. This leads to higher failure rates as these components regularly fail and are less efficient converting AC power to DC power. An Outpost rack uses a centralized redundant power conversion unit and a DC distribution system in the backplane. This is all handled.
Now, what's cool about this is, and what he's saying is, as a person who had the rack and stack, they pulled the power out and they rerouted it other places, so like you don't have to have a power cord going to the back of every single one. And you can see here, and then you can see here where they have the Ethernet drops, right? You can see all of that right there. You can also see right here there is probably a console connection. These are USB connections right here. This is probably more like a InfoBand. This may be a console. This one may either be a console or this one may be a console. Nah, that's Nick. This may be a console. I'm not sure. So when I say a console, meaning I can plug in a DB9 adapter or I forget what is it 242 R242, I think is what the number is on the actual cable, so that I can actually console in, literally like I can console into the actual server. All right. So that's what they're showing there, right? But again, this is like having a data center all in one inside your, say you could, if you was, had enough power in your house, you could order this and have it right in your own house. You just have to pay for the power and the cooling, but it's possible, right? But you don't have to get an AWS Outpost. They have a little smaller one. Azure Stack has one as well too. You can get an Azure Stack delivered right to your home. Of course, you're just gonna have to pay for it, but it can be done, right? So that was that. So we did some networking, and why all those things are important. So imagine, you having to do that at home. I don't know why this is still creating. See, I don't know. Whatever. All right, so let's go back to our course. I got 7 minutes. Networking. Okay. So let's go up here. Let's see if we understand here. Which number is the size in bits of an IP4 address? So that 192.168.1.5, that's what they're talking about. So how many bits is that? If we turn on all the octets, right? Right, it's 4 octets. 8 times 4 is what? Right, 32. Let's check. Boom. I said, which term determines how many leading bits in the IP address contribute to the network address? So they're trying to trick you here. Let's remove some stuff. I'm gonna help you. Have we ever seen anything called Netscope? So we're gonna remove A. Have you ever received anything talking about multicast? It's talked about, but it's not in this section, right? So we eliminated A and D, right? So net mask, subnet, and network. It says which term determines how many leading bits in the IP address contribute to the network address. So I think we want to eliminate network because that don't sound like I want to use that, right? And net ADDR is an actual command, right? It's an actual command. So I think we're gonna go with somewhere with B and C, and you all tell me, right, which one it is, B or C. Let's show solution. I might be wrong, might be network. NetMask. Remember we've been talking about NetMask the whole time. Remember that? The subnet mask. The subnet was the number of networks. There was these two right here could, if you want to say they could be the same, yes, because there's the number of networks and then the number of subnets that you get. So those two could be the same. We didn't talk about multicast. We never said anything about net ADDR, which is what you'll see from a rendering from a command on a Linux box. And Netscope was mostly out. So netmask had to be the answer, right? Now it says which address represent a valid IPv4 host address on a 192.168.0/24. Now remember, I cannot use the first and I cannot use the last of IP addresses on a network. So which ones are we going to automatically get rid of? We're going to get rid of 192.1.0, right? And just by sheer default and process of elimination, we would never have an IP address of 256, right? And by other process of elimination, we would never use the broadcast address, which is usually the 192.168.1.255 or 1.2.2, 1.2.3.4.255 is a broadcast address. So by process of elimination, we will eliminate all three of these because they don't make sense. So it will have to be A. Okay? Did that make sense how I broke that down? All right. Now here, I didn't go over IPv6 this week, but it was last week. I'm going to give you the answer. The answer is 128. That's how many bits it is. And that's in the book, in the chapter. All right. So I think we went through this. We're going to do a process of elimination here just by looking at it. I'm going to eliminate A I'm going to eliminate C. I may even eliminate G. So let's go to the chapter and see what is a valid IPv6 address. And we'll scroll down at the bottom. All right, so it says IPv6 unicast address is divided into two parts, a network prefix and an interface ID. The network prefix identifies the subnet. No two network interfaces or on the same subnet can have the same interface ID, right? And they also go in here to talk about the /64 and blah, 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 right? So here they show like 1, 2, 3, 4. So it looks like the first 4 octets are the network part, and then the interface is 1, 2, 3, 4 is the last. It's the interface ID. All right, so it says an equivalent of showing 127.0.0.1/8 as IPv6 is : 1/28. It says the unspecified address, I guess they got : then you want to do this one, you got : 0, unicast, see, here. This equivalent to all the networks ranging from 2000 through 3FF. And I just don't, I know some people use it. I think Google is using IPv6. I've never had a question on any type of interview that said, hey, write this octet or write this network inside of IPv6. I've never had that. All right, so these are their examples. Let me see. Do they give you like how to identify? I'm looking. No, it's very shady on this. So let's go back and see what the answer could be. So with knowing what we know now, what does not represent a valid IPv6? Maybe : does, because it could be. I don't think A does. Anybody else want to take a guess? No? Show solution. So the answer is F. I guess because of DB8 : 2. I'm not sure. I'll have to look this one up. We'll have to come back to IPv6. Okay. What terms allow one system to send traffic to a special IP address that is received by multiple systems? Well, it's not subnet and network and netscope and net ADR. I'm gonna say multicast. Who's down with D? Who's down with D?
Everybody's down with
Yeah, you know me. Let's check. Yeah, multicast. So multicast, like they say here, is one system to send traffic to a special IP address that is received by multiple systems. So let's look up here, multicast. Right. So to transmit a single message to a select group of recipients, a simple example of multicasting is sending an email to a mailing list. I have a group of I have a group of people. I have their email address. I'm going to send this information out. But if you're not on this list, you don't get my information. Versus when you're using DHCP, DHCP is gonna send out information everywhere. I don't care. I don't care. I'm sending it all out. What? Hear my roar. I'm gonna eat up all your network, and you gonna like it. Versus multicast said, "Oh, you're on my list. I'm so glad you decided to join me tonight, and it's a pleasure speaking with you. But here's a little information about me because you're on my list. It's a little bit more friendly." So telephone conferencing and video conferencing also use multicasting, but require robust protocols on networks. Video on demand services such as Netflix, Amazon Prime, YouTube all utilize unicast method of streaming. All networks within the internet support the unicast method for transmission. All right. Makes sense?
This conference will now be recorded.
Let me fix that. Uh-oh. Where's the thing yet? I'm trying to find it.